a Portland Community College mathematics telecourse. A course in arithmetic review produced at Portland Community College. Quite frequently in science and business equations, when one is required to do a long string of multiplications, generally it's the fact that the factors will all be the same. So what we wish to do here is simply to devise a shortcut way of writing a long expression where all the factors are repeated. The same thing. The agreement we will have, and agreement in mathematics quite frequently means a new kind of symbol or definition. We write the factor just once. And here's the agreement. To the right and up towards the top like a superscript, we count the number of times we wish this as a factor, 1, 2, 3, 4, 5, 6, and write that count up here. And we make an agreement. We say from now on when we do this, this simply means take this many of these and multiply them all together. That's the gist of this lesson. So this 2 with a little 5 written to the right and up high means take 5 2's and multiply them together. That kind of notation we will call exponent notation. So in a sense, relative to our desired problem, 5 isn't really a number, it's a counter. See, this means this, and there's no 5 here, but there is a 5-ness here. So this number that's counting the number of factors I'm going to multiply, repeated factors, that number we will refer to as exponent. The number here that's actually being used as a factor, that's actually doing the multiplying, we will refer to as a base. And the result of this multiplication, which in this case is 32, we will refer to as the power. So power is the answer. Exponent is the counter. Base is the thing that's actually doing the multiplication. We'll verbalize this whole process by the phrase 2 to the 5th power. You really begin to appreciate this notation when you consider something like this. This says take 300 of those and multiply them together. This would fit clear across the room. Now you might ask, does this problem ever occur that much? In business circles, yes, very much. In fact, this expression is nothing more than this. This number is 1 plus the interest rate, say on a house loan, and the exponent is the number of months, in this case, in 25 years. So yes, this exponent notation is used very heavy in business equations in particular. Now let's evaluate some expressions using exponent notation. The word evaluate, as we'll use it throughout this course, simply means find its arithmetic value. Now this reads 3 to the 4th power, which means take 4 3's and multiply them together. There it is. And 3 times 3 is 9, 3 times 3 is 9, and 9 times 9 is 81. This means take 2 5's and multiply them together, which is 25. This says to take 7 1's and multiply them together, and of course 1 times 1 times 1 times 1 forever is still 1. This says take 3 10's and multiply them together, which is 1,000. A very simple notation but very convenient. Now let's add to our notes some special definitions for special cases. Let's let the letter A stand for any whole number. By special definition, if a whole number has an exponent of 1, that's simply the same thing as that whole number. And if a whole number other than 0 has an exponent of 0, that will be by definition 1. Now these two might not make sense to you at the beginning. That's why we simply call it a definition. This is this simply because we say so. It makes the game of math work comfortably. Now in your algebra course, we'll look a little bit more about why this is so. But this says if I have something like 37 to the first power, that's simply 37. This says if I had 37 to the 0 power, that's 1. Anything to the 0 power is 1. That's simply a rule of the game that's made up. That's what we call a definition. Don't look for the logic at this point. It's simply a rule. Remember it. Now, the powers of 10 are special, easy cases. 10 to the first power simply means 10 because that's the rule of our game. 10 to the second power, which frequently you hear algebra people saying as 10 squared, simply means 2 tens multiplied together, which is 100. 10 to the third power says take 3 tens, multiply them together, which is 1,000. 10 to the eighth would be to take 8 tens and multiply them together. But there's a nice shortcut. Can you see it here? 10 to the first power is a 1 followed by 1 0. 10 to the second power is a 1 followed by 2 zeros. 10 to the third power is a 1 followed by 3 zeros. And indeed it is a case that 10 to the eighth power is a 1 followed by 1, 2, 3, 4, 5, 6, 7, 8 zeros. So 10 to the eighth power is another way of saying 100 million. 10 to the 13th power is simply a 1 followed by 13 zeros. Now let's see if we can verbalize that number. Units, thousands, millions, billions, 10 trillion. To multiply a number by a power of 10 is an easy special case, which is rather nice because multiplications by powers of 10 occurs very frequently in all sciences. And the trick of the shortcut is simply this. Append to the whole number as many zeros, additional zeros in this case, as is the exponent on the 10. So its exponent is 5, so we append 1, 2, 3, 4, 5 more zeros. Just that easy. Be cautious. When you get to decimals, we need to alter this rule somewhat. But with whole numbers, simply stick on that many zeros. To divide by a power of 10 is also a special, easy case. It is simply this. If you have a whole number with a lot of zeros on it already, just do away with as many zeros as you have exponent on the dividing power of 10. So we do away with 4 zeros, and that leaves us with 2,900. Now you might ask, what do I do if I don't have these zeros to undo? Again, in that case, we would become involved with decimals, so we'll save that case until the chapter on decimals. But it's just as easy. But the powers of 10 also give us another way of writing numbers which have been expressed in expanded notation. We can write this as 3 times 10 There's 1, 2, 3, 4 zeros, 10 to the fourth, plus 5 times 10 to the 1, 2, 3 zeros, exponent of 3. 2 times 10 to the second power, plus 8 times 10 to the first power, of course, plus 9. Now, this kind of expanded notation on powers of 10 will become a very important concept for those of you who go into computer systems, where one of the tasks you will be faced with is learning different number systems other than the base 10 system with which you're familiar. To get a feel for how much powers of 10 is used, consider this statement. A science book states that the distance from the Earth to the star Alpha Centauri is about this many miles. Very frequently, a science book will write numbers using powers of 10 and multiplications or divisions instead of writing the number in standard place value notation, which of course to the average person on the street might not mean much. So our task as a translator between the scientist and this man in the street is just what is this number in standard place value notation? And remember, we view this as making larger by this many places, or in the case of whole numbers, that many zeros. So we're going to append to this number 11 more placeholder zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's a distance from the Earth to the star Alpha Centauri, which, by the way, is the closest star next to the Sun. Let's see if we can read that. Units, thousands, millions, billions, so 25 trillion 500 billion miles from the Earth to the nearest star. When you get to extremely large number in science, this form of writing it is very, very convenient. So much so that if you look in almost any standard science handbook or textbook, you will see this form of number used far more frequently than this. So part of this lesson is to get you used to this exponent form of writing numbers. Therefore, some of the typical problems you will see just to get you used to this exponent form are simple problems like these, and to be able to verbalize them. So we read this 5 to the third power, and this simply means take this many of these numbers, there are 3 of them, and then multiply. So 5 times 5 is 25, times 5 is 125. Do not make the frequent mistake of thinking this means 3 times 5, which is 15. This is far, far more than that. So this reads 2 to the 7th power, which means take this many 2's, 1, 2, 3, 4, 5, 6, 7, and multiply them together. Now there's a bit of a shortcut here. 2 times 2 is 4, times 2 is 8. Let's stop. Here's another 3, that's another 8. So we have 8 times 8 is 64, times 2, or 128. Powers of 2 are used very frequently in advanced computer programming. They become very important there. Then 193 to the first power. Well, anything to the first power is simply another way of saying the base itself. At this point, this seems rather nonsensical, but later that indeed proves to be useful to us. And in this case, this is not, as many beginning students think, 0. Anything to the 0 power, by definition, is just another way of saying 1. So at this point of the game, just learn these two as to be memorized facts. Future courses will show the utility of this peculiar definition, that anything to the first power is itself, and anything to the 0 power is 1, with one exception. 0 to the 0 power is meaningless in our math. It just doesn't mean anything. It's not allowed. A problem like this asks us to review a point we learned in just a few lessons ago, to write this in expanded form. So this means I have 4 10,000s, and, which is plus, 7 1,000s, and 5 100s, and 3 10s, and 6. But now with our powers of 10, we can condense this a little bit and write 4, but instead of 10,000 in standard form, we can say 10 to the 1, 2, 3, 4th power, plus 7 times 10 to the 1, 2, 3 power, plus 5 times 10 to the 1, 2 power, plus 3 times 10 to the 1st power, plus 6. If we wanted to, we could say 6 times 10 to the 0 power, because 10 to the 0 power is 1, and this indeed tells me I have 6 ones in this position. This kind of notation is not only briefer and easier to write, but later in math theory, math for elementary teachers or math for computer sciences, this allows us to look at the possibility of having an entirely different kind of number system. And by writing a number in powers of 10, this will give us an idea and a clue as to what those other useful number systems might look like and how they might work. And dividing a number by a power of 10 means that this is going to get smaller by this many places. So by 6 places, so 1, 2, 3, 4, 5, 6. So dividing by 10 to the power of 6, in effect, does away with 6 zeros on the end, which in this case is all I had. This is going to give us a clue to going from a large number expressed in standard place value notation to a power of 10 notation. An example: the average distance from the Earth to the Sun is about 93 million miles. Rather than writing it this way, we could write it 93 times 10, and to get from 93 here, I'd have to make it bigger by 6 places, so that tells me the power of 10 is 6. And this is the way that it will normally be expressed within the scientific community. Slightly different than this, because when we get to decimals, we will alter this a little bit, but using the same principle. And at that this kind of notation with a slight alteration to account for decimals will be called scientific notation. And it will prove to be so important that most beginning science classes, be they earth sciences or biology or chemistry, will begin the first week of course discussing scientific notation as a way of writing very large or very small numbers. In fact, if you have a calculator, check your handbook and you'll find that even calculators have a way of putting numbers in or taking numbers out called scientific notation, which is nothing more than using powers of tens and later decimals to write extremely large or extremely small numbers in a very special and very convenient manner. This lesson begins you on that road to be able to do that. And thankfully, it's a very simple lesson. So let's just look at, in our few concluding moments, some math slang concerning exponent notation. There's a formula that says the area of a square. Now, the area of a square, of course, is a measure of the internal configuration, plane configuration of this square figure. And this says if you take a side times a side. So if I take a side times a side, there are two of them being multiplied together. So rather than writing it this form, we can write it in exponent form. This we have learned to read as of this lesson so far as s, whatever number it stands for, to the second power. But since originally we took a number times itself in order to compute the area of a square by actually just measuring the length of a side alone, we have verbalized this instead of s to the second power as the phrase s squared. So the phrase s squared is just a slang way in math of saying s to the second power. But this slang has been in math many, many hundreds of years, so it's not about to go away. So we need to get used to hearing this and knowing that it means this. So if in a college math course someone were to ask what is the value of 52 squared, what this slang is saying, the word squared, is 52 to the second, that's the squared bit, power. And this of course means take two 52s and multiply them together. And of course if we did that we would find it's 2,704. So we'd say 52 squared is 2,704. Another slang phrase you'll hear is the phrase cubed. For instance, in this question, what is the value of 6 cubed? Well, 6, and the phrase cubed means an exponent of 3. So to say 6 cubed means 6 to the power of 3, and of course that means take 3 6s and multiply them together, which has a value after multiplying of 216. The phrase cubes comes from the fact that if you were to take a cube, which means a solid, where all of the edges, the width, length, and height are all the same, so let's call it S for side, and we ask what is its volume, the formula for the volume is to take the side, the length times the width times the height, which is nothing more than S times S times S, because they're all equal, or the length of a side to the third power. So since this exponent of 3 was used first for computing the volumes of cubes, hence the slang word cube was used to mean exponent of 3. So you will hear both used interchangeably in math, and one needs to get used to it so that one can communicate with your fellow students and teachers. So if somebody were to ask what is the volume of a cube with an edge 10 centimeters long, that means I have a cube, which means all of the faces are equal, and the length of every single edge all the way around is 10. So I have 10 centimeters going up, 10 going across, and if we were to draw one little tiny cubic centimeter here, we're asking how many of these are in the whole large cube. And our formula said the volume is the length of a side or an edge cubed, or the side to the third power. But in our case, our side is 10 centimeters to the third power, and we can write this as 1 followed by 3 zeros. See, the powers of 10 have that special shortcut, and of course that's cubic centimeters, which in science we write this way. Whereas if we just said centimeters, we mean the length. If I say cubic centimeters, we mean these little tiny cubes. How many of them do we have? And this says 1,000. We could also ask concerning this cube, what is the area of one of its faces? And of course they all have equal area. and the formula we just had said that the area of a square, and each of these faces is a square, is the length of a side squared. So in this case, the length of a side is 10 squared. This means 2 10s being multiplied, or by using our shortcut power of 10, a 1 followed by 2 zeros. So the area is, and here is a small 1 square centimeter, so it's 100 of those centimeter squares. So we write this 100 square centimeter as opposed to 1,000 cubic centimeter, as opposed to a length which is 10 centimeters period, or centimeters to the first if you wish. I cannot underestimate possibly how important and how much this will be used in every single science or technology or business course you could possibly take. For instance, a typical problem in most business courses is this very simple problem for that course. $950 is placed into a savings account and allowed to compound annually at 6% per year for 18 years. How much will the original investment then be worth? In business mathematics or accounting, you will learn that there is a formula to predict this, and after you put the right numbers into the formula, it will look like this. And we aren't prepared yet to show you how to evaluate with this, but the point is, see, we have 1.06 to the 18th power, which means I want to take 18 of these and multiply them all together, and then that times that. That's a lot of work. But if we were to do that, we would find it would be $2,711.62. It's what that $950 would grow to in 18 years working under these conditions. In just about all business formulas, you will encounter exponents, and you must be able to work these. Of course, we won't actually take 18 of these and multiply them. A scientific calculator will have a shortcut way for us to do that. But we're quite a ways off from that. But part of this course is to get you ready to be able to do this soon, and the beginning of this is to become comfortable in exponent notation. So you won't be asked to do any problem like this for quite a while yet, but it's my way of saying that exponent notation is very important in the future. Do not slight this lesson because it might be new to you. This is your host, Bob Fennell, bidding you a good day until our next lesson.